Okay, sir. Good morning, sir. Namaskar.
Himanshu, oh, good to see you. Yes.
Recording टा सारे जो जितने start हो ना तितने ये करूँ सर मो 2 मिनट रे आछी 1 मिनट रे
अब ठीक है आसले स्टार्ट करिए आप
आगे
ठीक रेडी हिमांशु आर यू रेडी
हां सर
व्हाट्सएप पे पठेइबे So, welcome to the third day of the virtual lecture series. We are come to an end. It's the last day of the series. So today we have two speakers, Dr. Himanshu Shekhar Biswa, Associate Professor and Head of the Department, Niger Bhubaneswar, and Kumar Siddharth Keshav Bhardwaj, Associate Professor and Head of the Department, Ravenshaw University, Cuttack. So yesterday, Dr. Sudhanshu Tripathi is there, who is my teacher, and Himanshu happens to be my student. So it's a nice combination of young and experienced research persons. So before we start the webinar for today, I want to inform the participant that After the session, the feedback form will be shared with you. So everybody, it's request to everybody to kindly fill the feedback form, which will help us to improve in future. And also attendance sheet will be given at the end of the second talk. So now I request our today's president and our dean academics, the professor in charge of academics, Dr. Surekha Boyar Singh Madam, to welcome the resource persons, delegates, and the participants. Over to Madam Boyar Singh.
Thank you, Devashish sir. Eminent resource persons, Professor Himanshu Shekhar Biswal, Associate Professor and HOD, Chemistry, Niger, Bhubaneswar. Dr. K.S.K. Bharadwaj, Associate Professor and HOD, Chemistry, Ravenshaw University, Cuttack. Illustrious scholar Dr. Devashish Mohanty, convener of this excellent webinar. Assistant Professor and HOD, Chemistry of our college, the benchmark college in the district of Dhenkanal, that is Dhenkanal Autonomous College. Esteemed participants outside and inside the state, my dear colleagues and my loving students. Good afternoon and a happy welcome to all of you to this third day of the webinar of 3 days long web series. And in the absence of our brilliant leader, our principal, sir, Professor Ranjit Kumar Pradhan, who is on leave, I am delighted to be a part of this academic event and deliver presidential address. I am thankful to our principal, sir, to give me this opportunity, who is the most eligible and dynamic leader, the knowledge hub and eminent. I am especially thankful to the HOD, Department of Chemistry, Dr. Devashish Mohanty, who is the bank of boundless possibilities and hopes, for giving me an opportunity to be associated with this excellent program. I appraise Dr. Devashish Mohanty, who is a token of inspiration, a good organizer, illustrious scholar, writer, research guide, best teacher awardee, and most importantly, the administrative bursar of our college. And he is to set benchmark for others to follow. I expect that under his leadership, the Department of Chemistry will attain the height of success. We are really privileged to have amongst us two eminent professors, two eminent scholars, proven personalities, and knowledge bank, Professor H.S. Biswal and K.S.K. Bharadwaj. We are happy and we have good fortune that we are going to avail their service and we are going to share their thoughts, experiences, inputs, and so on. Their presence in this webinar will heighten and add to the gravity of this webinar. And on behalf of this college, once again, I take this opportunity to welcome you all to this very significant academic event. I am sure that they will deliver the goods and they will catch the expectations of our participants. It is exclusively meant for UG students, teachers, and this particular lecture aims at giving the participants an opportunity to know the basic principles of spectroscopic technique use, and I am sure that our two versatile experts will address the issue and they will rise to this to the occasion and they will make the students interested and engaged on the topic basic spectroscopic technique use for tomorrow's scientists. I am sure that their talk would be very significant, inspiring, insightful, and outstanding, and very useful for the participants as well as the researchers. Thank you all and welcome you all once again. Thank you. Over to Devashish sir.
Thank you, madam, for nice welcome address. So now we have both the research persons with us. I welcome Dr. Siddharth Bhardwaj, sir, who has also joined. Previously, Himanshu sir also joined, and also with us, my teacher and guide, Professor Sajdar Samal, sir. So I welcome all of you. Now I request our Deputy Controller of Examination and HOD Sanskrit, Dr. Sanjit Kumar Mahapatra sir, to give an introduction to our first speaker, Himanshu Shekhar Biswal. So the first speaker will be Himanshu Shekhar Biswal. After the introduction speech, the talk will be started.
Thank you, Devashish Babu. So it is a privilege on my part to welcome Professor Dr. Himanshu Shekhar Biswal, who is now working as Associate Professor in Chemical Science, Niger, Bhubaneswar. He has completed his Masters in Chemistry from Utkal University. He has done his PhD under the guidance of Professor Sanjay Watgankar, Tata Institute of Fundamental Research, TIFR, Mumbai. His postdoctoral research was with Professor Michael Mans of CEA, Saclay, France, and Professor Jennifer Ogilvy, University of Michigan, USA. He started his professional career as inspired faculty at National Institute of Science and Research, Nigeria, Bhubaneswar. His area of research interest includes conventional and non-conventional, non-covalent interactions, laser spectroscopy of jet-cooled biomolecules, salvation and isomerization of peptides and proteins, computational inorganic chemistry and catalysis, astrochemistry, ionic liquids. He has a distinction of getting several honors and several awards. Some significant honors and awards conferred on Dr. Biswal are Inspire Faculty Fellow by INSA DST New Delhi, India, in the year December 2011, Dr. P.K. Bhattacharya Memorial Award, Indian Society for Radiation and Photochemical Sciences, ISRAFs, BARC, India, in the year 2011, and many others also. He has more than 50 publications in international journals and more than 100 in the national journals. So to add his credits, he has also guided many students for the PhD degree under his supervision. Welcome to you, sir, to this virtual lecture series 2022 of day 3 on basic spectroscopic techniques for tomorrow's scientists, organized by Chemistry Department of Dhenkanal Autonomous College. Over to Devashish Babu.
Thank you, sir, for your kind words. Now I request our first research person, Dr. Himanshu Shekhar Biswal, to present his talk.
Okay.
I want to inform you that they have developed certain modules and virtual practical laboratory, which will be helpful to the undergraduate students of the states. So Himanshu sir will demonstrate some of those modules, and I hope we can collaborate with him, and so that in future our students can get benefit of it. Thank you, Himanshu sir. Now over to you.
Okay, sir. Can you enable the host, the participant screen sharing? It's disable screen sharing. I cannot share the screen. Okay. Now it's working. Okay. So it's visible. Okay. So thank you, Devashish sir, for inviting me for this webinar. I also thank all the faculty members of Dhenkanal College, the students, seniors, juniors, for giving me the opportunity to present something different than the research what I do here. So here what I'll do actually, so this time I'm taking a online laboratory courses. So in Niger, what we do, we actually we record the video and share with the students. I found it's not very convenient, and I recorded the first day I recorded the video for 5 minutes, and the size was about 350 MB, and it's impossible to record 3 hours of class and send to the student. So I thought instead of by recording the video, they are not getting an opportunity to touch the spectrometer or the cubate. So instead of that, I'll do the same thing virtually. Actually, they will have a virtual laboratory. So we thought of developing a model so that the student can do whatever they can do the spectroscopy related experiment in the laboratory, except putting the cubate or sample holder in the spectrometer. So today I'll talk about that. So it is called Village, and I gave the name Village. Actually, it is meant for to reach the remote students who don't have a privilege to access these high-end spectrometers. So we have planned to have around 10 experiments of a different spectroscopy, UV visible, IR, NMR. So whatever available here in Niger, and display them to the students. Actually, this is written in LabVIEW. LabVIEW is the software, but for this you don't need to buy the software. There is a executable file. We have converted our course to the executable. So you can just double click the executable, it will work. So you don't need any software or any third party software to run this one. And one you need the runtime machine, and that is freely available from LabVIEW. And once you install this one will work. Okay. So since the title of the seminar is basic spectroscopy techniques for tomorrow's scientists, so today I'll cover a little bit about the basic principle of UV visible spectroscopy and IR spectroscopy. And most of the talk will be on actually the software or the modules we developed. Okay, so this is for the students I have made. So electromagnetic radiation, each range of the radiation, electromagnetic radiation have associated with one or two spectroscopy. So I have given a sample. This one, this figure is taken from Thomas Angel's quantum chemistry and spectroscopy group. So if you look at, so this is gamma ray, X-ray, ultraviolet, visible, infrared radiation. It comes from higher energy to the lower energies. And these are the few spectroscopy listed here in the table. These are the few spectroscopy we use as a chemist, we use in day-to-day to carry out the research. So if the electromagnetic radiation as the light source, I'll come to that, will be the electromagnetic radiation of radio wave. The spectroscopy to be associated with this one is NMR spectroscopy. If it will be microwave in this region, we'll have a rotational spectroscopy. If it will be in the infrared region, we'll have vibrational spectroscopy. We call it IR spectroscopy, more popularly known as IR spectroscopy. If it will be visible and ultraviolet region, we'll have illuminant spectroscopy, or we call it UV visible absorption spectroscopy. So what we need actually for the basic components, the spectrometer, if I get a time, actually I'll show the spectrometer, how it is getting built. So it's very simple for any spectrometer. So you need three sources, actually three components. One is the light source, other one is the sample cell, the third one is the detector. Okay. So as I said, the light source for us is electromagnetic radiation, and we work in the lower part of electromagnetic region. So here for UV visible light, I can have a lamp, actually general lamp or the stuff, or the lamps are used here. So I have a light source. then these are the class light actually. It can have radiation for all wavelengths. So to select the particular wavelength, we put a monochromator. Okay, so monochromator is nothing, there is a grating actually. So it's selected because of the diffraction, different wavelength will have a different path of diffraction. So because of that diffraction, you can select a particular wavelength and pass through the sample cell. And depending on what we are measuring, we can measure the transmitted light, we can measure the observed light. So that's how we can measure depending on our need. So we can take those lights to the detector and detect it and measure it. And in a simpler way, this is how we can represent the electronic states here. Screen pointer. Okay. So this is the ground state electronic state. This is the excited electronic state. The ground state electronic state could be S0. S0 stands for the singlet ground state. The excited state will be S1, the singlet excited state. So there is also possibility of having the ground state triplet state and the excited state triplet state. So what will happen if you have a light of a UV visible radiation? The photon energy is sufficient enough to take the electron from the ground state to the excited state. Okay, so that one, not all the photons will be absorbed. Some of the photons will be absorbed, and the rest of the photon will be transmitted. So if you look at here in this diagram, I have a cuvette with a path length of L. I have the incident light which is coming from the light source, which has intensity of I0. Or the initial intensity. When it passes through the cuvette contains the chemicals, the organic molecules or inorganic complexes. So when it passes through, some of the lights actually, some of the photons will be absorbed by the molecules, organic molecules here, and the intensity will be reduced and the rest will be transmitted, and it will fall on the detector. And the detector is nothing but a photomultiplier tube, and we measure the voltages and we digitalize it and record it. Okay. So this photon actually comes in the UV range. Okay. So I can have the small wavy stuff here. These are the vibrational states. Within any electronic state manifold, you will have plenty of vibrational states. And these wavy stuff, small one corresponds to different vibrational states. Okay, so I have a vibrational state starts from vibrational quantum number, starts from B is equal to 0, B is equal to 1, B is equal to 2, B is equal to 3, B is equal to 4, and so on. So if I have a light, it can have a transition from B is equal to 0 here to the excited state. Vibrational level will be 0, 1, 2, 3, and 4. So I have a very vertical transition. So B is equal to 0 in the ground state to B is equal to 4 in the ground excited state. That's why I have a very strong intensity for the 0 to 4 transitions. Okay, there are other transitions are possible, and these intensities are less. So this is actually if the students will learn more, so they'll get to know this is called Frank-Condon lab. So you have a very good Frank-Condon lab between 0 to 1, 4 transition, and that's why the intensity is huge in comparison to other transitions. Anyway, so forget that is a little advanced level. So for the time being, I guess all of you know this Beer-Lambert's law. Sometimes they call it Beer's law also. So Beer-Lambert's law, it says the logarithm of, it's again the natural logarithm of I0. I0 is my initial intensity before passing through the cuvette, divided by I is the transmitted light, which is equal to the epsilon, C, and length. So the C, okay, so epsilon is the molar extinction coefficient. It depends on the molecules. It is an intrinsic properties of the molecule. Whether you take 10 molar or 20 molar, it doesn't change. If you have one molecule, it will have same molar extinction coefficient. Or 100 molecules also will have the same molar extinction coefficient. So it's like intrinsic property of the molecule. Okay. So this C stands for the concentration. So I can have a concentration here. The L stands for the path length. So mostly available cubit, and most of the time we use the cubit of path length 1 centimeter, so that the equation becomes very easy actually. So if you multiply 1, so I have molar extension coefficient and the concentration. Okay. So this is some basic components of UV visible spectroscopy and some little basic principle or fundamental concept on the UV visible spectroscopy.
Well, and the meeting source 6টা বাজে মু আর তারপর যাবিনি
Okay, so next, okay, so what I'll do, so the program we have written, actually the software we have written to determine the molar extension coefficient. So the molar extension coefficient is not that easy to determine. So we have to prepare different concentrations of the molecule you want to determine the molar extension coefficient. You have to have a different concentration of the solution. Then you record the UV visible spectra, and this is called observance. Logarithm of I0 by I is called the observance. So if I plot the observance in the y-axis and the concentration in the x-axis, and it looks like a linear plot, and that the slope of that linear plot will give me the molar extension coefficient. So the software we developed to illustrate, to find out the molar extension coefficients of the aromatic amino acids. So before that, I'll introduce a little bit what is the amino acids. These are called alpha amino acids. Why alpha amino acids? It contains acid group as well as the amino group. So this is the acid group. Close to the acid group is called alpha carbon. So to the alpha carbon of the acid, the amino group is attached. So these are called the alpha amino acids. Okay. So there are 21 amino acids, naturally occurring amino acids. But we are not interested, not all of them observed in the UV visible region. So these are the 3 aromatic amino. There are actually 4 aromatic amino acids, which contains the aromatic ring in the side chain. So we have phenylalanine, tyrosine, tryptophan. So they have in biochemistry they use 3-letter code for to represent the amino acids. If it is phenylalanine, they write PHE, or they write 1-letter code. So if it is phenylalanine, they use F as 1-letter code, tyrosine as Y, tryptophan as W, histidine as H. So these are the amino acids. So I'll be concentrating on these 3 amino acids to find out what will be the molar extension coefficient. Okay. Okay, so let's go to our visual laboratory, the village. So as I said, you don't read as village. So it is village, actually it is meant for the village students. So that's why I have given the name. So there are 2 versions, one for the student version, other one is for the teacher's version. The TV stands for the teacher. So I'll first click the student version. Okay. Just a minute. Okay. So here I'll click and it will go directly to my software. Okay, so it's asking, taking the permission. Okay, so what here I need, I have to put the my name. This is the login and password. And this is what the password we use. This is the login. Okay, so here comes everything. So whatever I detected, here you have a light source, then the light source will pass through a monochromator grating, then the slit will be there, then the rotating disc will be there, so that I can take one of the light to the sample cell, the other light to the reference cell. And these are the cubit we use it. Okay, so one is used to keep the sample, the other one is used to keep the reference, so that I will always record the I0 by I at any wavelength. so that I have a observance. This is how the spectrometer look like. Okay. So what I'll do, these are the compounds. I have plenty of compounds, L-phenylalanine, L-tryptophan, L-tyrosine. These are the amino acids I'll choose. I have different concentrations. These are the different concentrations I'll choose. Then I can do the measurement. Okay. So if you have an option of doing experiment in the laboratory, so what you would have done, you would have taken this molecule, find out the molecular weight, and add the amount of water, actually the required amount of the water to make this concentration. And once you have the solution, you put it in the solvent, you put it in the cubate and place it in the
It is not visible. Himanshu, it is not visible.
Which one? This one?
No, nothing is, only the first UV tutorial V15 extension is coming in the screen, not the experiment.
This tryptophan is coming, right?
No, nothing is coming.
Nothing is coming.
Nothing is coming.
Yeah, only the screen of the previous one, the UV tutorial V15.
Okay, let's. Okay. So I'm stop sharing. I'll share that one, that screen. Fine. Okay. Sorry. Is it now? Is it visible now?
Yes, it is now.
Okay. So this one, I said I have a compound selected. So I have 3 amino acids I kept.
Please tell it come fast again, because students are not out there. Mulu ko. It doesn't dekha out there.
Which one? This eta ko outre koibi.
এই जो स्क्रीन टा आउथरे टिके एक्सप्लेन करो
स्टार्टिंग
जेतु देखि नांती पिला
हां स्टार्टिंग रो एक्सप्लेन करछि
हाय
सो आई हैव अच्छा what are koibi ki so I have different compounds here. There are 3 compounds. So as I said, we'll do the we'll find out the molar extinction coefficient of phenylalanine, tyrosine and tryptophan. To find out the molar extinction coefficient, I need to prepare different concentration of those amino acids. Okay. So to do that, here I have given the select compound. Compound means I have phenylalanine, I can select it. I have a tryptophan, I can select it. I can tyrosine, I can select it. Okay. So this let's select the compound L-phenylalanine. Okay. So here I can select different concentrations. This 1000 stands for 1000 micromolar concentration or 1 millimolar. This is 900 micromolar. This is 800 micromolar. This is 700 micromolar. Okay, so I have 700 to 1000 micromolar for a phenylalanine. Okay. So here I have mentioned the path length. So this is the path length of the cubate used here in the experiment. And all the solutions are prepared in water. So if I ask somebody, the student, to prepare this solution, so this concentration of this compound, then what I do, I'll take weight of some weight of this compound, the phenylalanine. Then I'll add appropriate amount of water to find out this to make a 700 micromolar solution. Okay. Or if I know the volume, I have to make a 5 ml of this one. Then I'll go back, I'll measure the accurate amount of this one, accurate weight of phenylalanine and dissolve in water. Okay. This is how I can prepare different solution and place this one in the cubate. So we'll have a reference cell here. So the reference cell placed it here and the sample cell is placed here. And at every wavelength, I record I0 by I. I0 will come from the reference cell, I will come from this one. Okay. So and the reference cell only contains water, and I place both of them in this one, and after that this software, whatever it will do, and the instrument does the same thing. Okay. So what will here I have something called start button. If I start, the spectra will be recorded. So let's start. Okay. So it is going from a longer wavelength to shorter wavelength. So in terms of energy, actually we have done going from to a small energy, lower energy to higher energy. You can do other way, that's not a problem. Okay, so this is the phenylalanine at 700 micron. Okay. So if I increase the concentration, let's say 1 millimolar, 1000 micromolar. So definitely, as we expect, as we are increasing the concentration, the observance maximum here at this wavelength will be more. Okay, that's what we expect, and we are going to see that also. Okay, so this peak is coming here. Yeah, so you can see there is a huge difference in the observation intensity or the observance at this position. Okay, this is 257 nanometer. So this is the x-axis is the wavelength in nanometer, y-axis is the observance. Okay, so I can select tyrosine, the other molecule. So here, since its molar extinction coefficient is huge, we have taken 200 micromolar for tyrosine. I can start it here. So any guess, the students? You can see. So the tyrosine, the absorption happens at 275 nanometer, the maximum. Okay, and this one, and the observance is huge. Okay, in comparison to tryptophan, you look at the concentration is 200 micromolar only. So here the red curve is for phenylalanine, which concentration is 1 millimolar, 5 times more than this. So if you look at a tryptophan, if I take a 60 micromolar, even less. Okay, so when the instrument is recorded, the indicator becomes red. When the record is complete, it becomes green. So still this indicator is red, you cannot do any manipulation here. Anything is some analysis here. I'll show what type of analysis you can do. Okay, so the tryptophan absorption is huge, very broad absorption. The observance is also huge in comparison to anything. So look at this is the red one is 100 millimolar, sorry, 1000 micromolar means 1 millimolar of phenylalanine. This is just a tyrosine, 200 micromolar. This is again 60 micromolar of tryptophan. So you can see this is a very nice example to find out the molar extinction coefficient of different amino acids. I have different concentrations. So I'll plot the observance versus the concentration. I'll show in the next model. So here we have lot of options. So I can zoom. This is the horizontal zoom. I can zoom this peak. This is horizontal. I can zoom it. Okay. If you have a very small one, this is bring back to the original one, the full spectrum. I can do the vertical zoom also if I wish to. Okay. So this is the vertical zoom. So I have a cursor. If I really want to record or find out what is the maximum. So in the cursor positions are here, this is 257.13 and the observance is 0.20. So reading the cursor position, you can find it out the observation maximum, the X value and Y value, and you can record the observance. And the next step, you can verify the Beal numbers law by plotting observance versus this one. Okay, so this is the student model. The student will do this experiment virtually, selecting the compound, selecting the concentration. Then they will plot actually observance versus concentration fit linearly to find out the slope will be the molar extinction coefficient. There is another teacher's version, so where the analysis is given. So what I'll do, I'll stop sharing this one. I'll go to the teacher's version. Okay. So I have a teacher's version here. Okay. Okay, so let me share now the screen. So this one is a teacher version. So here, let's go to this one again, start. So there is an analysis button here. This is disabled now. I put the analysis button and you can do the analysis. What students will do in their home as a homework, the teacher can do here itself. The software is written for that to verify, to check the answer sheet, everything. Okay. So I show that one. This is just we are developing. It needs little more work. Okay, so now the analysis button is enabled. So I click this analysis button. So here I'll plot. That's what I was telling. The y-axis will be observance. The x-axis will be concentration. It in micromolar. If I say click the plot button here, so you can see the 4 or 5 lines corresponding to different concentration. So this one, after doing the 5 recording the 5 spectrum, you can plot it. You will have a plot like this. Then if you click the fit button, it will fit like this. And the slope, you can find it out. So the slope is not represented. So the slope will be 200 around. So you can find out the slope. And the slope will give you the more about the idea about the molar extinction coefficient. Okay. So these are the 2 versions we have developed till now. And there are many other small experiments we are doing so that the student can use it and have a feeling of this one. And this teacher version we are not giving to the students so that they can do it by their own and to find out what will be the slope on the stuff. Okay. So this is about the UV visible to find out the molar extinction coefficient. If I have time, I can go to some other model. Can I? Devasis sir.
Devasis sir. It is 4:20 now. Maybe 4:30 up to 4:30 you may continue.
Okay.
Oh, you go on 4:45.
4:45.
Okay.
4:30, 35, you go on talking, then 5 to 10 minute discussion.
Okay, so let's say I'll go to the IR part. I'll skip. I have a lot of more slides, so I'll skip this one. I'll go to the IR part. So this one is fine, the UV visible one. So I'll go to the IR. Okay, I'll stop. We have different models. I thought actually I gave the hyperlink. I thought it will work. So it's not working. Okay, so I have IR modules also. Okay, so let's share the IR module and explain the students. Okay, so here, okay, sorry. Let me share the screen. So we have also IR module here. So here in IR, what you will do, you have to make the pellet actually, right? So if you have a solid sample, you can make the pellet, or it's liquid also you can do. There is another method to do it. It's not a problem. Gases also you can do it. So you have to press this one, the sample, to make the pellet. Then you put the pellet, put this one in the pellet holder. Then you have to use the KPR window for that. So these are the how put the window here on the pellet holder. Then you mount it here, and there are way of recording. You can have a mode of recording. You can record the IR spectra as a transmittance or this observance. So what IR spectra will give? IR spectra will give the bond vibration information about the bond vibration. So here we have planned to find out the cyclic, the CO stretching actually from the IR spectroscopy. If I know the CO stretching, okay, the frequency of the CO stretching, from that I can find it out the force constant. Actually, that force constant reflects the bond strength. More is the force constant, more is the strength of the bond. Okay, so you will have a cyclopropanon, cyclobutanon, cyclopentanon, all the stuff. And we can record the IR spectroscopy, find out the frequency of CO stretching. From that frequency, I can find it out the force constant. Just looking at the force constant, I can tell whether this CO bond is stronger or more strength, has more strength compared to the cyclobutanon. Okay. So here the observance we recorded as observance mode. Here we can record this one as a transmitting so that your peak will be downward, the disruptive style. And here you can have two options, and there is nothing wrong or recording in observance. So sometimes people ask why the IR spectrum is downward. So it's not true. In old days, the detectors were not developed in that way so that you can measure the observance. So nowadays there are a lot of detectors, very sensitive detectors are available. You can choose both of them, both the modes of recording. Okay, so I'll record one of them, cyclopropanon and cyclobutanon. So let's start here. So this one we started from 1200. So cyclopropanon, you will have CO stretching, CH stretching, then bending, so all the stuff will be. But the CO stretching will be huge. I don't have time to explain why the CO stretching intensity will be more, because it has a very strong dipole moment. Okay, C double bond O. So the CO stretching will come around 1800 wave number, 1850. So these are given in wave number, centimeter inverse. So you will have a huge peak at this one, and this corresponds to the carbonyl stretching, C double bond O stretching of cyclopropanol. And you can find it out the force constant K, which is equal to 1 divided by 2 pi C. C is the velocity of light. The nu is equal to, the frequency is equal to 1 by 2 pi C, then square root of force constant K divided by the reduced mass mu. Okay. So if I know the frequency, I know the velocity of light, then I can find it out the force constant. Okay. So these are the small CH bending actually here. This is the CO stretching. So we'll have a CH stretching around 3300, 3400. So as long as this indicator is red, I cannot do anything in the screen, this screen. After it is done, then I can zoom it up and find it out also. Zoom it up the small peak, which are not visible, both vertically and horizontally, and find it out the peak positions. Okay, both intensity as well as the wave number, x-axis and y-axis values. Okay, so there are small CH stretchings are coming here. Yeah, these are small, the CH stretching and the 3000, above 3000 wave number. So here you can do whatever you do the text with the PC up attached to the spectrometer. The same thing where you can select the mode, then the scan, all the stuff, same thing we are doing. You can analyze like this also, except putting the sample, you can do whatever you want, you can do this one in the software. Okay, so now it is green, so the recording is finished. So as I said, I can zoom vertically. This peak is not visible to me because of this one auto scale. I can zoom it off, vertical zooming. Then these are so close, I cannot find it out the exact position. I can zoom horizontally. So I can zoom so that I can find out the exact position. Then I'll take the cursor here to find out this position, which is 1418 wave number. Okay. Then I can go back to the full spectrum. So I'm interested of CO stretching, which is the big peak here, the strongest observed, the strongest peak here. So I'll zoom it here, zoom it more so that I'll have exact information about the position. So I put this one, my cursor here. It's about 1450.5. Okay. So as I said, if I know this is the wave number, the frequency of this one, the CO stretching, I can find it out the force constant. So this is the teacher version I have loaded. For the student version, they will go and put the formula and find it out. They will first calculate the reduced mass for these vibrations, the masses responsible for this vibration. For here, the carbon and oxygen are linked. So I have to take mass of carbon, which is 12 mu, mass of oxygen, which is 16 mu. Then I can find it out the reduced mass. the students will do manually, then they will find it out they know the frequency, they'll find it out the force constant. For a teacher, we have an analysis button here. So what we can do, as I said, I'll put the mass, put the wave number, which is 1850.5. Okay, so what are the atoms involved? Here my atom is carbon. This carbon is stretching I am looking at. Here the atom is oxygen. Then if I say calculate, it will find it out the force constant. It will find it out the reduced mass, the force constant. Okay. Oh, sorry, it is 1850. I'll calculate again. Okay, so the force constant for us cyclopropanol, you remember, is 1384.14 centimeter Newton meter. Okay. So should I take one more example just to compare?
Yes, Steve.
Cyclobutanol.
Yes.
Okay. So cyclobutanol I'll take. So let's start this one. So remember the cyclopropanol comes at 1850.5. Let's see where the cyclobutanol is coming. So what will be the force constant? You can find it out force constant for other stretching frequencies, bending frequencies by using this analysis. This is a teacher's version, not the student version. So the transmittance will be huge, around 1800 wave number, and we'll see whether it is the wave number is more for cyclobutanol or less in comparison to cyclopropanol. And this is the question I'll give to the students. If it is more, why? If it is less, why? They'll find it out. So it looks like it is less. It comes in between 1800 and 1850 wave number. So definitely it's less than the cyclopropanol. And there should be some reason. The force constant for carbonyl stretching in cyclopropanol is huge. That means the bond strength is more in comparison to the bond strength of CO in cyclobutanol. Okay, these are the CH stretching around 3000 wave number. Okay. So it's done. We can do the analysis here. So before that, what I'll do, I'll zoom it up, find out the exact position of this one, zoom further, so that I can take the cursor here. Exact position is 1820.5. So I'll put it here. Remember, it's a 1385 force constant for the cyclopropanol. So here I'll have 1820.5. This is again the same atom. I don't need to choose oxygen, carbon, and oxygen. I calculate. So it reduced to the 50 nanonewton per meter was actually reduced. Earlier it was 1385. Now it is 1339.40. Okay, so it's about 45 Newton per meter. The bond strength decreases. Okay, this is a simple demonstration. If I really want to find out the CH also, I can do it. Okay, so let's say for this P, if I want to find it out the force constant, so vertically I can zoom it up. Okay, little vertical more. Can find it out the position here. So it is 3038. I'll put 3038. Then the carbon 1 is C, carbon 2 is A, hydrogen. And if I calculate, I can find it out. It's a 505. It says actually the CH bond strength is less and C double bond. Okay, so this is all about the software, brief introduction. So we are developing 10 such experiment, one student version, one teacher's version. Hopefully, I'll make it ready and make available to all the college students in Odisha, maybe outside Odisha. Okay, so I'll with this, let me go to the slide. I'll thank my students for their effort making this one. It takes a lot of time actually. So I will acknowledge my student. Actually, this one is made by Akshay, who is here. As a pointer, this is this guy. He's working, making the instruments also, writing the code. So he has made all the software. Okay. So I thank you for your kind attention. This is a beautiful view of Niger. So I encourage the BSc, MSc students to visit Niger. If think about Niger, if they get some opportunity, try to do your BSc or MSc. So, okay, so I'll let you know most probably next session. The chemistry department is going to start integrated PhD program. Integrated PhD means after BSc you can be enrolled in Niger as a PhD student. So that will be starting soon, and hope to see some of the students from Denkanal College in Niger. Thank you for giving me opportunity. Thank you again, sir.
Thank you. Thank you very much. If any queries, you can raise your hand or type a question in the question answer box. And there is one question from our student, that is there any module for NMR? Yes, proton
Yes.
NMR.
Yes, there is module for NMR, there is module for fluorescence. So I told these are the three already till now we have made 3 modules. Or not 3, actually 6 modules. One is basic, another is application. So we have made 6 modules. So one is UV visible, other one is 2 for UV visible, 2 for IR, 2 for fluorescence, 2 for NMR, and what else? So 8 ho gaya. So we have 8 now. We may take another for BTs or materials chemistry related module. Okay, so NMR module is there.
Okay, thank you. So I will definitely, it will be helpful for the students of Odisha. With us, Professor Sardar Samal is there. So I will request sir to summarize this topic within few minutes. Then our second speaker is ready. Professor Bharadwaj will listen to his talk. So I request now Professor Sardar Samal sir to summarize this topic.
Himangsu, please unshare your slides. Okay. Uh, uh, you can see me?
Yes, sir.
Okay. So thank you, Professor Vishwa. It is really fantastic. Really fantastic, because I used to see this kind of calculators readily available, but not with so much of realistic details. I have been long ago, say 25 years ago, I was working in this kind of machines myself. And then I was wondering, like, is it possible that we have interactive modules where our students can take training? Now you have made it possible. A very big thanks from all of us.
Yes, yeah.
You have made life a lot simpler for our students.
I'm very sure while teaching the theory courses also, some teachers will use it to show the spectrum.
Yes, absolutely. And then the other things which I would like to suggest that you need to add, or you may add in future, is that this small calculations like MOPAC and PM5, people, our students, they do not know actually. This molecular.
So this is regarding the experimental part.
I understand that, because these are all soft training. Not only you have this FTIR and UV, NMR, and associated with structure. How about associating with the structure these MOPAC calculations? They're very simple, no? Easy, freely available. But most of these calculations, our teachers, students.
Definitely, one day I will present that.
So, like you create the XYZ files and then or PDV files, and then generate the structures, or from the structures you get the coordinates, and then those kind of things you can even automate or simulate like this. I do not know how you will do it, but some kind of visual training is required. If this is the structure, then how we go ahead with MOPAC calculation, integrated with Chem3D or ChemDraw, and integrated with yeah. So you understand what I mean. If that can be done, it will be also very good, because right from the structure they can calculate. Already in ChemDraw it is there. You have the structure, you predict the FTR spectra, predict the NMR spectra, and so they will run the experiment in your virtual machine, and then they will predict the NMR or FTIR or UV from ChemDraw, and then they can match it. Okay, so this force constant calculation or whatever, they're simply fabulous and fantastic. Okay, only one query I would like to make: this carbon oxygen bond. You gave carbon as atom number 1, oxygen as atom number 2, but there can be a single bond as well as a double bond.
Yes.
Normally, in this force constant calculation modules which are available, they give an option for choosing whether the bond is single or double, and accordingly the force constant value slightly varies.
Okay, so what they shall do, they use the Morse potential. So here we have done only simple harmonic oscillator to make it simpler.
I mean, I understand. What I see is that the program recognizes the bond order. When you run it, the program automatically understands that this is a carbon-oxygen double bond. That's exactly what. So, okay, it's fine. But it's maybe that is a little doubt from my mind. Like, if there is a single bond, what will happen? If there is a double bond, what will happen? The force constant value will change, definitely. Anyway, so
yeah, so there is other way here. The known is frequency. So we can find it out to have empirical relation with the distance. Okay. So here the known is frequency. We are finding out the force constant. So there are known parameter is bond length. They can find it out the force constant.
Okay. So there some clarification maybe somewhere in a note you can give somewhere, like the module automatically recognizes that it is a carbon-oxygen double bond. it's not a carbon oxygen single bond. And then it's automatically accordingly calculates the force constant.
Sir, it's maybe it's a the absorbance itself takes into account whether it's a double bond or single bond.
That's what I told. I was explaining the CH single bond and C double bond O. So I didn't have a C single bond O. Okay, so I'll put one.
What I do is, that's what I'm telling. You take an example of a C single bond O compound and a C double bond O compound, structurally very closely related.
Yes, here, sir, we have few. I only displayed only one example. We have
I understand, and I do not doubt your the authenticity of this thing. What I need to say, I wanted to tell you is that comparison should be between the single bond and a double bond, how it changes, how the strength changes. So I'm really delighted that you are doing wonderful job. I know developing this kind of programs or software is a very difficult, so it takes a lot of time to write the programs, and maybe you will find out a way to share it. I saw it in your Facebook. But how it should reach the masses, that is very important.
I'll make it free. I'll sell. I'll be Karodpati item. So
because this is
10 rupees for one experiment.
10
experiment, 100 rupees. And you think there are lakhs of undergraduate and graduate students, PhD students.
So this is a copyrighted material. Yes, copyrighted material. So it should be available, and please see that the students can easily access it. Whatever be the manner of. Okay. So
we're working actually. There are small glitches are there. Working, making it beautiful, so that will make the manuals also, so that our students can use it, or teachers can use it also.
How about you put all these programs in a dedicated website, in your own website, put it in a dedicated space, these interactive models and all the details, like your.
Yes.
That will be, I think, somewhat easier. Like, we know that this is the site where you visit, you see all the kinds of programs available. I can download anything, and if there is any payment to be made one time, or that can also be done. So, but the colleges can do the supervisor.
Himanshu is quite rich, sir.
And
no, I am not rich.
Siddharth, you can do it.
They are actually rich family in our area, so we are from same. Very close by villages.
Yes. So what happens, the problem is that in the undergraduate colleges where there is no research but only theoretical teaching, the government can also make a provision for buying such kind of things. With the approval of the government, one can buy it and demonstrate to the students. So all these things are possible. You have to only think how to make it feasible. You have to think a bit and maybe consult with those personnel who are in higher education. They can integrate this thing. I mean, government can subsidize it heavily or make it free for all the undergraduate colleges and pay you. That is not I think, very difficult job. So anyway, I'm really delighted, extremely delighted. As all the time I have been telling that this say UV, which is known since say maybe I do not know 100 years or so, or machines were available at least 50 years before, and good machines were available some 20, 30, 40 years before, good machines. But till today, our students, majority of our students have not seen it. That is a really touching situation. Like we are a nation of highly intelligent people, but do not have access to the basic things. IR, UV, these are all basic tools. Everywhere it is the minimum thing that one should have. Students do not know or have not seen a quartz vessel, cuvette, and they do not know if it is a solid film, how to take an UV, if it is not a solution, but it is a solid. transparent or colored solid film, or if it is higher, is there any how to make a caviar pellet? Nothing is unless. So that is my concern, that we after so many years, and in this age of 21st century, we do not have access to basic teaching tools. These are very basic, very elementary things. So Professor Vishwal, I mean, really, my heart goes out to you, to all your students. You have really done a marvelous job, at least in this critical situation where future is very much uncertain. I mean, future of higher education in our state is not yet very much predictable, which should have been much better than what it is now. I think this particular endeavor will go a long way in helping our students. Please keep it up, refine it, and maybe make it as cheap as possible, so that a student in
I'll make it free, not cheap. I'll make it free.
Yes, you're given appropriately the name village. A student in the village can access it and understand
we are making one advanced level 1, and I have kept the name as Gram.
Okay.
Yeah.
Gram. Okay. Village and Gram. Very good.
Yes.
So thank you. And from my side and from everyone's side, all the participants, and I thank you very much. This is extremely useful, and please make it simpler and easy to access. That is the only thing. Thank you, Devasis, for giving me this chance to speak a few words. Thank you.
Thank you, sir. So thank you, Himanshu. Now it's time for our second talk. Now I request our Dr. Sanjit Kumar Mahapatra sir to give a formal introduction of our second speaker, KSK Bharadwaj.
Thank you, Devasis Babu, for giving another opportunity to introduce another distinguished resource person to this virtual lecture series 2022 of Chemistry Department. He is Dr. KSK Bharadwaj, Kumar Siddharth Keshav Bharadwaj, who is currently working as Associate Professor of Chemistry with additional charge of Head of the Department Chemistry in this Ravenshaw University, Cuttack. He has more than 10 years of teaching and research experience in the extended field of materials chemistry. To his credit, he has 25 publications in peer-reviewed journals. He has already completed PhD in the year 2007 from Indian Institute of Technology, Kharagpur. His thesis work was based on studies of super paramagnetic particles. His postdoctoral work is at KAIST, South Korea, consisted of vapor phase deposition of silicide nanowires, their ensemble magnetic property, and single nanowire magnetoresistance. He further moved to Research Center for Integrated Quantum Electronics, that is RCIQE, at Hokkaido University, Japan, where he worked on semiconductor nanowire growth on pattern structure and single nanowire lasers. He has special interest in popularization of science through community outreach programs. His current research interest is focused on designing heterostructure materials for energy-related electrocatalytic processes, understanding the descriptors that control the activity of the catalysts, development of electrochemical biosensors. I welcome you, sir, to the virtual lecture series 2022 of this day 3 on basic spectroscopic techniques for tomorrow's scientists. Now over to Devasis Babu.
Thank you, sir, for nice introduction. Now I request Dr. KSK Bharadwaj to present his topic.
So is the slide visible?
Yes,
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 sir.
yes, visible.
Okay, thank you for giving a nice introduction. And I also thank the HOD of Dhenkanal Autonomous College Chemistry Department, Debasis Bhai, for giving me this opportunity to interact and to talk about mass spectroscopy. Actually, you have already learned from Himanshu sir that how the spectroscopy he related with different wavelength of electromagnetic radiation or energy of electromagnetic radiation with that of different spectroscopies like UV, IR, NMR, or all these spectroscopies which you saw till now in the earlier session, it was associated with some electromagnetic radiation, and it was the interaction of electromagnetic radiation with matter. It absorbs due to either vibration or rotation or electronic transition. A electromagnetic radiation is allowed to fall on a matter and it interacts with the matter. Then we see again the electromagnetic radiation where it is absorbing or where it is emitting and or where it is transmitting. And from that, we try to know the structure of the molecules or structure of the compounds that we have taken in it. But mass spectroscopy is although called a spectroscopy, but it is, to be very frank from the beginning, that it is not a interaction of matter with electromagnetic radiation. It is just named spectroscopy because this is also a very helpful tool in knowing the structure of the molecule. That is why we call it a spectroscopy. Otherwise, this should not be confused by the young students that it is also a interaction of electromagnetic radiation with matter. You have seen in the list shown by Himanshu sir that the mass spectroscopy was not there actually. So what is mass spectroscopy? That we will try to understand it, the basics of that. Here what we do, we take the molecule that you can see the M written here, and we bombard this molecule with some energetic electrons. We prepare some energetic electrons and they travel and bombard with these molecules. And once the molecule is bombarded with electrons, this molecule is bombarded, either this can lose electron or it can gain electron. So you know that in every organic compound, there is either a single bond or a double bond or a paired electron is there. So everywhere through the bond also there are paired electrons, or there are lone pair electrons. We call some lone pair electrons. Like in ammonia, you have on nitrogen you have one lone pair. In oxygen also you have lone pair electrons present in the molecules. And once one electron is taken out, or when electron is bombarded, it loses one electron, then it becomes a molecular ion, what we call as molecular ion, or M plus dot. We call it M. It becomes a dot and a plus. The pair breaks in that sense, so it becomes M plus dot. This molecular ion is formed. This is a positive ion is shown. There can be also one, it can gain also one electron to form one M minus. But the whole molecular, this mass spectroscopy deals with these positive ions. we are not concerned about the negative ions, although it is formed there. But the maximum number of ions formed is this positive ions, and we try to know what is the real structure from these positive ions. And it does not stop here. M plus dot doesn't stop here. In the second line, you can see that this M plus dot can again further break to form M plus, M1 plus and M2 dot, or M1 plus dot and M2. So these are called daughter ions. Daughter ions because these positive ions, or this again plus dot odd electron ions, they can again further break. So one molecule, once one electron is dragged out from that, it may further break into smaller fragments, and those are called daughter ions because they can also again further fragment. And we actually design one instrument to find these positive ions, to recognize these positive ions. So this is on the right hand side, you can see the instrument, the inside of the instrument, or how the instrument looks like. Here on the bulb, you can see the dots there, black dots there. This is the molecule we want to really take the mass spectra. This is in a high vacuum chamber. Those molecules are there, and they are made to the gaseous state, and then they are allowed to the second chamber, this chamber 2. Here you can see that the filament is there. The one is filament is written. That is the negative part, and other side is the positive part. That plate is there. And this is connected with a power source. This filament and the other side, they are connected with a power source. That's at the middle, you can see. This is connected with a power source where we can adjust the voltage. And as we change the voltage, here, electrons start moving from the cathode to the anode, and as electrons start moving here, those are shown by the blue lines. They strike with the molecules that are coming from here. They strike with the molecules. And once they strike with the molecules here, they form this plus dot, or molecular ions that form, and that also further undergoes fragmentation. And inside this mass spectrometer, what we see that there are plates. There are these plates, you can see the repeller electrode, and another is written accelerating slits or repeller electrode. Here it is written. These are nothing but positively charged plates. We have put some positively charged plates, and once positively charged plates are here, that means there are some plates which is charged positive. So what they do, they repel. The name is itself shows that it's a repeller, and it repel the positive ions that forms, and repel with the repel with a particular speed or a velocity that that depends on the charge that is produced, the charge that is there on the molecular ion or the fragment ions, and also the voltage of this repeller. So this repellers, the repeller that is placed there, they have a certain voltage, and they repel the positive ions, and those positive ions start moving in the opposite direction through this tube. And once they move through this tube, then it's made an arc, or you see a circular path, an arc is made. And here a magnetic field is applied. Here you see that magnetic field 500 to 8,000 Gauss of magnetic field is applied. What does this magnetic field does? When these positive ions are produced and they are repelled through this tube, then you know that when a charged particle moves, it also produces a magnetic field. That means when electricity passes through a wire, if you take a compass near that, it deflects. So same way, here when this positive ions they pass through this, they produce a magnetic field around them. And if another magnetic field is placed outside, then this will be deflected. The magnetic field around this ion will interact with the outside magnetic field, and they will deflect, and they will take a particular path. What is the path they will take, we will discuss. And this magnetic field, I will further discuss this part. But the job of this magnetic field is to separate the positive ions as per their m by z value, mass to charge value, m by z value. This magnetic field has one purpose. The purpose of this magnetic field is to separate the positive ions as per their m by z value. That means one molecular ion is produced. From that, different daughter ions are produced, and those daughter ions also have positively charged, but they have different m by z values. So with the difference in m by z values, this deflection can really separate them out and can leave one after the other. By changing the magnetic, we can allow one by one the positive ions to this detector. And this detector, what this detector does, the detector only counts. That means it only counts the number of positive ions. It does nothing. Whatever the positive ion that is coming, it counts the number of positive ions, and we know the m by z value by this amount of field we are applying. And from this detector, we know the number of positive ions those are coming. So the mass spectra, you can see from the left hand side, this is the mass spectrum of this ethane. It's a simple molecule, ethane. And this ethane, once it is bombarded with electrons, this becomes a plus dot. So this plus dot, we have written it here because we don't know from where it is lost. This may be from any bond, any CH bond or any CC bond. This one electron has been lost by bombardment of outside electrons. And this is called the molecular ion in ethane. And then this molecular ion can further break. This CC bond can break, or this CC bond can break. So this can form this kind of a M by Z 29 with C2, 2 carbon atoms, or with 1 carbon atom, or with 3 carbon atoms and 1 hydrogen less. Like this one plus dot also, C2H4, it can also break. So there are different ways this can break, and they will break and reach the detector. And the detector will just count that what is the number of ions of that particular positive ion that is coming to the detector. And it will make whichever have maximum number that is coming to the detector, it gives that the real, then we make a graph of relative relative abundance versus the M by Z ratio. So on the x-axis we take M by Z, and on the y-axis we take relative abundance. This relative abundance is the availability. Kete achi, kete ta aschi gote particular ion. So here you can see the 29. 29 means this one C2H5. C2H5 plus. This is M by Z 29, and this is the maximum number of this one is coming to the detector. And so the relative abundance of 29 is taken as 100. Here you can see that the relative abundance is 100, maximum number. And in comparison to that, what is the number of other ions those are coming? That is 28 is coming, almost 60% relative abundance. And this one maybe 29, and then 44, the molecular ion. Here the molecular ion peak, 44 is almost 30% of the relative to the 29, the most abundant peak. Similarly, 43, 44 and 43 is there. And then there is a peak for 15 as well. There are also after 28, some 27, these peaks are there. Then there is a proton loss. So 2 proton less kind of structures they come. So if I take the mass spectra of ethane, then I will get this kind of a spectra, where you will see that on one side M by Z, and on other side the relative abundance. So after getting this kind of a spectrum, we try to find out the structure of the compound. So from here we come to know that it is 44 is the molecular ion peak. So what may be the structure of the compound? So we go the other way. We have an unknown compound. Here, as I explained, I have taken this ethane, and then we break it and see these components and try to explain these components. But actually what we do, we take a compound, we don't know what is its structure, or we have some guesses only that what may be the structure. But after the molecular spectra, mass spectra, from the molecular ion peak, we say that this may be the molecule, or this may be the molecular mass of the compound. So this is just the other way around, where we have an unknown molecule and we take the spectrum and try to analyze it. So to understand the structure from this kind of a spectrum, what we get is this kind of a spectrum, and from that we need to draw the structure. So to do that, we must know what are the fragmentation patterns, how molecules really fragment in such a condition. So this I have already explained. And so basically the mass spectrometer is made up of these 3 components. One is an ionizer, where you take the sample and you bombard it with electrons. This is called electron ionizer. There can be different ionizers, but here we bombard it with electrons, and then positive ions are formed, and the positive ions are made to move forward by giving another positive charge, by placing a positive charged plate near it, where it repels the positive ions. and then that moves through a mass analyzer. Mass analyzer is nothing but a magnetic field, as I told you. And the job of the magnetic field is to segregate the different masses, the different M by Z, it segregates, and allow one by one, with different M by Z value, allow one by one to reach the detector. And the detector does nothing but counts the number of positive ions coming at a time. So from that, we draw the graph of M by Z versus the relative abundance. Relative abundance, because abundance with respect to the maximum, that one ion, which is the number is maximum, that we take as 100. So it is not, it's about the relative abundance, relative availability. So the ion which reaches in maximum numbers to the detector is the most stable positive ions, which reach that, therefore it reaches the detector. The maximum number of that reaches the detector. Others also reach, but they reach in less numbers. So this positive ion is more stable, and it reaches, or more amount of this positive ion is formed. We have also double focusing mass spectrometers, where we have an electrostatic analyzer and a magnetic analyzer. That means that positive ions are allowed to pass through one electric field, and then with a then also in a magnetic field. So when it goes through already we know that when a charged particle moves, it has a it is charged, so it has a electric charge around it. So if I put it in a electric field, it will deflect. And again, in a magnetic field also it will deflect, because a moving charge is having magnetic field around that. So it is kind of a more strict analyzer, where it very specifically it allows positive ions with specific M by Z value. It's very specific in that sense. So presently what we see around us is this double focusing mass analyzers. So as I was talking, that what really this does, this electrostatic field, that repeller, we have put one repeller, that's a positive charge we have kept, and that positive charge plate we have kept, that has a voltage of V, and Z is the charge of the ions that is formed. So the energy that we are giving to the charged particle, the plus charged particles, the plus charged particles, that the energy we are giving is ZV. V is the voltage of voltage of the repeller, and then after getting this energy, that moves, so that moves to that a kinetic energy is given to that, so that's equal to half mv square. Here V is the velocity. So this V is the velocity, and we know that when magnetic field B is applied, there is a magnetic centripetal force, and the magnetic centripetal force deflects, and a moving matter, when moved in a curved surface, it has a centripetal force as well, centripetal force which tries to throw it out, and the centrifugal force is there. The centrifugal force is given by the magnetic field, that is ZBV, and this is mv square by r. V is the velocity here, and here if we just solve this equation, the m by z, we will see that b square r square by 2v. Here b is the magnetic field, applied magnetic field, and of course V is the voltage, that the repeller's voltage that is applied. So by tuning this B and V, we can change the R, and for a particular M by Z value, and a particular M by Z value for a particular value of B and V, the R is constant. That means for a particular M by Z, if we tune this B and V, we can allow through that tube, because that curved tube has a particular R. And through that R, only one M by Z can cross when we fix this B and V. So at a time, only one positive mass with a particular M by Z value can really cross through that tube, through that turning. Others will just take a different R and will strike the walls of that tube, that turned tube. So only one can really go through that turn at a particular B and V. Here, generally, we fix the V value and change this B. That is the magnetic field we change. And by changing that magnetic field, we can allow one by one the different positive ions that are formed. But there is a limitation in mass spectrometer that we cannot really separate the M plus or another molecular or another ion, another daughter ion with 2m mass and 2 plus charge. So these two cannot be separated, because the M by Z for both of it, both M plus and 2m2 plus, will be the same. So we cannot really separate this. So this equation really tells us that how a mass spectrometer operates, and how different ions with different M by Z values are separated and goes to the detector. And here you can see the molecular ion peak. We have taken the an example of pentane. So mass spectrometer or mass spectrum of pentane is given. Here you can see that 72, and this 72 is also the molecular ion peak for this pentane. And another example of benzene is given. Of course, in benzene, we see that only most probable electron loss from benzene will be the electrons. Those are the pi electrons that are there in benzene, and this will be lost. And if you have an heteroatom, then there are lone pairs, and there is most chance that the lone pairs lose electrons, as it is shown in alcohol, in a ketone, in an amine, or if it's a double bond, then there is a the most probable electron is the pi electron in the double bond. So these are the probable electron loss to form molecular ions, and those molecular ions, they show peaks. Here, like benzene shows the molecular ion peak at 78, and here pentane show the molecular ion peak at 72. That another very important factor is those ions, those are formed, they must have some lifetime to reach the detector. If they don't reach the detector, then my detector cannot really see any ions. So that must have a lifetime longer than this 10 to the power minus 5 seconds, so that if it reaches the detector, then my detector can see it. So if you have very bulkier if you have bulkier molecules where the molecular ion is not very stable, then we don't see the molecular ion peak. It is not necessary that we always see the molecular ion peak. We may not see also the molecular ion peak. We may see only fragmentation pattern, but not the molecular ion peak. Devashish bhai, how much time do I have more?
You continue
Achha.
till 5:45, 6. It's
Okay. Okay. So another factor is you know that we have that every in an organic molecule you have carbon, hydrogen, and also this bromine, chlorine. There are different other elements also present. Even if you take carbon, then there are C12 carbons and C13 also. So there is a probability that one of the carbon here may be C13. So if it is C13, one of the carbon is C13, then what we will see, along with a molecular ion, we will see a M+1 peak. That means one M by Z value higher than the molecular ion value. So we will see a mass value higher than that of molecular ion peak. So even if one proton is replaced by one hydrogen is replaced by a deuterium, then also you will get one M+1 peak. Again, if you have one carbon C13 and another deuterium, you may see M+2 peak. So like that, if you have isotopes, so we will see certain isotope peaks. These are called isotope peaks. These peaks are seen at higher values than the molecular ion peak. They are called M+1 or M+2 or even M+4 or M+3 peaks. So when you see that there are certain peaks with M by Z higher than the molecular ion value, that means your molecular mass is showing 78, but you are seeing some peaks are 79 or 80 or 81, then you must know that those peaks are due to the isotopes present, either C13 or deuterium, or if it is here an example is shown that with bromine in the molecule. Bromine actually exists in two isotopic forms. One is 79 and another is 81. And you can see that their natural abundance is given here, almost 50%. That means if from the nature you take 100 bromine atoms, what you will see that 50% of that is 79 and another 50% is 81. So the two isotopes 79 and 81 are equally distributed in nature. So if I take my bromoethane here, then my 100 molecules of bromoethane, 50 will contain bromine 79 and 50 will contain bromine 81. So I will have both M+ and M+2 peaks, and the relative abundance here will be almost 50-50, almost of equal height. I will see peaks for M plus and M plus 2 at equal heights. These equal heights, so that they are of equal abundance. That means the natural abundance of a particular element decides what will be the peak ratio of M plus 1 or M plus 2, or these ratios are decided by the natural abundance of the elements. So here the case of bromine is given. So if you see that there is one M peak and M plus 2 peak of equal height or equal relative abundance, here relative abundance, equal relative abundance, 2 peaks you see, then you can easily say that your compound contains bromine. This is by seeing itself you can say. So if you have a M plus peak and M plus 2, then you can easily say that your compound contains bromine. So this is taken from the Kemp book, and here you can see that natural abundance is shown if hydrogen is 99.985, the deuterium is 0.015%. That means if you take 100 also, you don't find one deuterium. In 1000, you will find 0.1. In 10,000, if there are 10,000 hydrogen atom, the probability of one deuterium is there. So your peak will also be similarly, if there is one hydrogen atom, then the other peak is 0.015% of the first peak. If it is the relative abundance of molecular ion peak is if 78 or any value, for the 79, it's very, very less. You cannot really see. So one proton doesn't make any difference, and you will not see actually a M plus 1 peak. But in C12 and C13, you can see that it is, C13 is almost 1%, 1% of the total. So if there is one carbon, then if the molecule, with respect to the molecular ion, the M plus 1 peak will have 1%. So if you have 10, then it will become 10%. So 10 carbon atoms are there in the molecule. So accordingly, the M plus 1's this thing also increases. Here you see certain values like chlorine. Chlorine 35 and 37 have a natural abundance of 25% and 75%. Chlorine 35 and 37. So that means almost 3:1 ratio, their natural abundance is there. And in bromine, as I have already told, it is 1:1 natural abundance. So in case of chlorine, there is 3:1 natural abundance, 35 and 37. So you will see another M plus 2 peak with M and M plus 2 in 3:1 ratio. If there is one M and one M plus 2 in 3:1 ratio, then you can blindly say that there is a chlorine atom in it. So this is an example of chlorine, 2-chloropropane. 2-chloropropane has a M plus and M plus 2 peak with 3:1 ratio. The height ratio is 3:1, you can see here. Okay. Similarly, here in another daughter ion is also formed. And the molecular ion, it breaks to a daughter ion. The CC bond breaks here. CH3 dot goes. And then the chlorine side has a mass of 63. And you see 63 and there is also a 65. So this isotope peak is not only there in case of molecular ions, but also there in daughter ions. So, and they are more prominent in case of this chlorine or bromine is there, because their natural abundance is quite high. That's the main point here. Here the life is little more complicated. If you have 2 chlorine atoms, then what will happen? See, you may have both the chlorines 35, then you get the molecular ion peak. You may get 135 and 137, then it will be M plus 2. If both 37, then it is M plus 4. So you will get M plus 2 and M plus 4. These 3 peaks will be present. But what will be their ratio of relative abundance or the height ratio of relative abundance? We find that they follow a pattern. And that pattern can be clearly understood if you take A plus B whole square. And here they are in 3:1 ratio, 35 to chlorine is 3:1 ratio. So A is 3 and B is 1. And A plus B whole square, you know, A square plus 2AB plus B square. Here A is 3 and B is 1. So it is 3 square, 9 is to 6 is to 1. A square is to 2AB is to B square. So the 3 peaks will be in the ratio of 9 is to 6 is to 1. You can see that it is 9 is to 6 is to 1. So if you have 2 chlorine atoms, then it is A plus B whole square. If you have 3, it is A plus B whole cube. And likewise, it continues. So if you have this molecular ion peaks and M plus 2, M plus 4, this kind of peaks are there, then you can go for, and they are so much prominent, then you can see that whether they are chlorine or bromine is present. And here also another isotope peak for bromine is considered. Here 2 bromine atoms are present in a molecule, Br2. So the Br2 molecule itself has 2 bromine atoms. So here also, because 2 are present, it is A plus B whole square. But here 2 bromine atoms, natural abundance is 1 is to 1. So A is 1 and B is 1. Their natural abundance ratio decides the A and B. A is the isotope with the lower mass value, and this is the isotope with higher mass value. So 1 is to 1. And then if I do A plus B whole square, then A square plus 2AB plus B square. This is 1 is to 2 is to 1. So the ratio will be 1 is to 2 is to 1. You can see 158, 160, and 162. 1 is to 2 is to 1. So if you have 2 bromine atoms, your A and B value is 1 and 1 because of the natural abundance. And you can put the formula of A plus B whole square and find out the ratio of M plus 2 and M plus 4 peak. Okay. There are certain ions. I will go to the first maybe to understand a little bit better. Here, let this molecular ion or a daughter ion, M plus dot, is formed here. But while going on the way, it actually breaks. It's not stable. While it starts as M plus dot. But while going on the way, it's not that stable and it breaks into 2 parts. It has gained certain velocity due to this propeller. Because of the voltage of this propeller, it has gained certain velocity. Now this velocity is distributed between these two ions. One may be neutral, one may be positive. So this M plus, which is actually on the way to the detector, if it is getting fragmented, then that fragment is having some other velocity, because that velocity is distributed between the two ions. It is some other velocity. Then if it would have been formed, this M plus would have been formed here, it would have got some velocity. But because it is fragmented on the way, it is having some other velocity. So my detector, my analyzer is confused with these kind of ions. These are called metastable ions. The metastable, the name metastable itself is quite maybe new for you. You know, one is stable and one is unstable. And this stable and unstable we term in terms of thermodynamics, that is free energy and all that. But metastable is something with a relative stability. Like a ball on a table is stable, but if I move a little bit, then it will drop. So little change will take it to the stable phase. So these are metastable ions. Those have relative stability. They are not unstable completely. They have a relative stability. They go some distance. Then on the way they break. So these are called metastable ions. They on the way they break, and they take also the turn in at some particular magnetic field. They take the turn and go to my detector, but but that is not the particular M by Z. This equation does not satisfy them, because this V that one has with that V they got this kinetic energy, but on the way it breaks, and the fragment, one of the fragment which is positive ion, is really going further and reaching the detector and giving me some confusing results actually. And we tried to analyze those results, and these are called metastable ion peaks. And we see certain peaks which are not from any fragments, any possible fragments, but we see certain peaks. How can we explain that? That we tried to understand that there are certain metastable ions which have relative stability, and on the way they are breaking. So the velocity is also distributed between the two ions. So my analyzer is not properly detecting it and leaving it. So these are the metastable ion peaks. The ions in a mass spectrometer, I have written something, you just forget about that. So if I see certain, my ion is M. This is the metastable ion. I should have got a peak here, but I am getting actually the peak here at M star. I am getting a peak at M star. Actually, this M is breaking to this small m, but I am getting a peak at M star. My M is getting fragmented to this small m on the way, but I am getting this peak at M star. So how can I understand this M star? I understand this M star by a small calculation, that this is M2 square by M1. M2 is the real fragment that is happening, M2 square by M1, or here I can say that this M2 square by M. So you must understand it, that my real molecular ion is M, which is getting fragmented to small m. So I should have got it at M, but I am getting it at M star because it is not directly this M, this small m. If it would have got the got near the repeller, then it would have got a different velocity. But because it is breaking at in between some point, it is getting the velocity is getting distributed, and it is getting some velocity. So I am getting it at M star. So if you are getting at M star, then you do that M1 square by M will give you the value of M star. So this M2 square by M1 or M square by M from this, the M square by M will give you the M star. So that's the, if you are seeing certain peaks, which is not matching with any of the fragments, so it's not in any possible fragments that is possible from that, then that must be coming from the metastable ion peaks, and you take some two values and try to find out because of which particular mass you are getting this M star. So I hope you will read it and try to understand it in better way. I tried my best. So this is also, there are certain examples I have taken that dodecane is a long chain hydrocarbon. It can break at any possible CC bond or CH bond. And we can see that there are a lot of fragmentation patterns, and all these patterns can be seen. And so basically, to understand this, although we need to understand this molecule, this mass spectra with what is happening inside, organic chemists take molecules and they put it in the mass spectra and see certain fragments. And after getting those fragments, they try to analyze what is the molecule and what are the possible fragmentation patterns. So we try to also make what are the possible fragmentation patterns. So here an example is given that if you have an heteroatom in the molecule like chloride or oxygen or Nr or CO, then I have already discussed that the electron will lose from the heteroatom. And once the heteroatom electron is lost, then there are three ways of cleavage. The cleavage way, the first way is there may be a breakage of CY cleavage. The heteroatom and Y may get cleaved, or there may be this alpha cleavage. Alpha to the Y position, this RC bond will undergo a cleavage. Here you will see that certain arrows are drawn with complete arrow, and one is half arrow. The complete arrow is movement of 2 electrons, and the half arrow is movement of 1 electron. So either by also 1 electron movement or 2 electron movement, you can show this these fragmentation patterns. So another is alpha cleavage, RC cleavage here. Another is the HY cleavage, the H that is in the beta position, beta carbon atom, that gets cleaved, and the HY that moves completely away, and there is a double bond with plus dot there that is formed. So these are the three kinds of cleavage possible if you have a heteroatom on the this thing. So we must know the fragmentation pattern of different molecules, and that's also in your course, that how to see the fragmentation pattern of different molecules. So this is a ketone, and how the fragmentation pattern occurs here. You can see that this CH3 is lost. This CH3 is lost here. CH3 dot is lost here. All this may undergo a cleavage here, or may undergo a cleavage here, and those are the two big peaks here, 83 and another is 43, 83 and 43. 98 is the molecular ion peak. One is 83 and one is 43. We generally write it as M minus 43 or M minus 83. One fragment is going out from that. So molecular ion M minus that fragment, the mass of that fragment. We write it in that way also. So here the situation of a alpha cleavage of a alcohol, you can see that this alpha cleavage CH3CH cleavage is occurring, and you will find it at M by Z 45. And another interesting thing in the mass spectra is about the nitrogen containing compounds. If you have one nitrogen in the molecule, then you know that each carbon is joined with 4, it's tetravalent, but nitrogen joins with 3, and its molecular mass is odd. So if you have an odd molecular mass, then you can say that it is a nitrogen is there, odd number of nitrogens are present there. So if it is even, if a molecular mass is even, odd number of nitrogen, then odd molecular mass, and if you have no nitrogen, it's the molecular mass is even. But if you have one nitrogen or odd number of nitrogen, then you have a the molecular mass is odd, and you will find a M peak. Here you can see that the 87, a odd number for a molecular mass, and you can say that there is nitrogen present in the molecule. Similarly, another nitrogen containing compound I have given. Should I end here?
Okay, we'll give 5-minute discussion.
There are McLaughlin rearrangement and others, but they can see that, and they can take a further example. Okay, I thank the organizers, and also my teacher is Sasodhar sir is there, so it's a tensed moment for me. So I think I end here. If we take some questions.
If anyone has any questions, they can raise their hand or can write their question in the chat box. Question answer session.
But Himanshu has made a very nice module for all the spectroscopies. I request him to do it for mass also, if that can be. There may be different kinds of codes they have to write for mass.
Probably no question. I want to request you, if you can share this slide. I will share with the students. And second thing, I want to another request that since Ravenshaw University has both NMR and IR spectroscopies, we should have our students should give a chance to see those instruments. So we will make an arrangement like study to Ravenshaw University and kindly allow our students to see at least the NMR machine, the IR machine, and how they are operated. It's a request.
It will be our pleasure, Devashish bhai. You please arrange the students to come, and please let me know after before 2-3 days so that I can arrange certain experiments also. They will not only see the machines, they will do certain experiments. Either at least 1 or 2 IR and 1 or 2 UV experiments they will do. And also the UG, if they are UG final year students, they can see the NMR and do certain NMR, 1 or 2 NMR instruments, 1 or 2 NMR samples they can do.
Thank you very much.
We will be glad to do that.
Okay, we will definitely collaborate with you. And
please tell the students to come, and if you bring them, we will be glad to arrange it. But just before 2-3 days, inform us so that we can make the arrangement.
Yeah, we will definitely inform. Now I request Sajdhar sir to kindly tell few words about the presentation of Siddharth.
As we saw yesterday and day before yesterday, today also we had two great teachers. Their lectures are so fundamentally strong. There is nothing much to comment about, except that I would just like to add that there has to be a kind of nodal center. Like we have NMR there or UV there, we can mass spectroscopy, mass spectrometers are not very cheap. They are somewhat expensive, like multi-mass spectroscopy, multi-mass spectrophotometer or ESIMS. They could be a little bit expensive, but I think, Siddharth, if it is possible, you can move funding agencies. You should have one multi-mass, because that, unlike NMR, doesn't require anything except that you have a laser source and computers and all that. Just simple air conditioning and the machine works fantastic. So maybe give some projects with like Professor Naik is there, Vice Chancellor, and he is working on polymers. So molecular weight determination in multi-mass of polymers, molecular weight of polymers using multi-mass is one of the preferred methods. Small molecules are okay, fragmentations and all that, rearrangements and all that, so well understood. But there is a challenge when it comes to polymers. So I had some hand-on experience with how to determine molecular mass of polymers who are difficult to undergo ablation under laser conditions. So maybe, in our state, there should be at least one center where there should be a molecular mass facility, determination of molecular mass, high molecular mass, maybe of 1,000 and more, like that. And of course, you will have small molecules. That machine can handle also small molecules. Now we have Ravenshaw University, which has some machines. We have NISER, which has many machines. We have IM Mineral and Material Institute. They have many machines. We have CPAT here. They have many machines. Machines are plenty, So, and I have talked personally to all. I have talked to Himanshu. Will you allow students? He said yes. I talked to a couple of friends in IMMT. They also say gladly yes. And of course, Siddharth says that it is simple. I talked to Smita and CPET. She readily agreed. No problem. Any kind of machines they can have a look. So it is only the basis. It is your responsibility that you do something with the government. And there was a time when all the BSc students were taken on a study tour. Okay, so that that was a part of industrial chemistry, and that somehow is scrapped now. So when you move a particular college with a group of students, move from place A to place B, if that is recognized by the government, I mean, if that is a part of the curriculum, then it becomes more interesting. Okay, so that all over the state the students get some this kind of exposure. So that is my suggestion to Professor Bharadwaj, Professor Mahanti, Professor Vishwal. All of you are very dynamic. You have I mean very crystal clear vision. So how about frequently discussing together and devise a foolproof method so that this facility of visiting advanced labs and doing experiments there become official, a part of the curriculum. Okay, Devasis. So with these words, I would like to thank again Professor Bharadwaj. He, as usual, he's a terrific teacher, very accurate and very pinpointed. He has fantastic voice modulation, and he has done a very wonderful job. I thank Professor Bharadwaj for this lecture. It is definitely very much inspiring. I would always say that, like yesterday, all the students should be given a window to directly interact with the resource persons. What I would suggest Denkarnal College to do is to have all these lectures as links, YouTube links in your website, so that anytime the participants can log into your college website or department website and link into these lectures. And also you provide the contact details of all the resource persons there in that page, so that the students can directly interact with the teachers through email or even phone and discuss their their problems related to this kind of lecture. This is a fantastic endeavor, Devasis, you have started. I think this is only just the beginning. Others should follow suit, and other colleges also do the same thing. You are in two capacities. You are now important. You are also representing the government college teachers, and also you are the secretary of Odisha Chemical Society. So that way you have access to the government, impressed upon the government that this kind of study tour to the national, to the advanced research centers should be a part of the curriculum. Devise a method by which this will be practical and feasible. And then you continue this pursuit, not only in Denkarnal College, in other colleges also, so that in spite of our meager resources, our students remain informed of the latest things. With these words, I thank you again for giving me this chance to summarize this today's lecture. I wish that this platform should remain open, and we continue this from time to time. Thank you, Devasis, for giving me this chance. Thank you.
Thank you, sir, for your kind presence for the 3 days. You have sitting there whole 3 days for all the sessions, and the commitment level you have should inspire all the young students. And I am very much thankful to all other research person. Today is the end of this 3-day lecture series. I have planned it because we are organizing many seminars, webinars, conference, but all those are in research fields, higher research fields. Generally, the students of undergraduate and postgraduate level don't benefit much from that. Therefore, I thought to organize a lecture series based on the topics of the undergraduate classes, and I think it will be definitely beneficial to the undergraduate students. More than 500 students have been registered, and not only from Odisha, from some students are from outside Odisha also registered and participated in this webinar. And as the all the talks are recorded in YouTube, live streaming is also done through YouTube, and they will be always available in our website, so students can go at any time and watch those videos. And also I will share the PPTs and material shared by the experts to the students in the WhatsApp group and through their mails. And certificate will go given to the participant who have participated in all 3 days. It will take some time. In a week time, all the participants will get the certificates. And again, I am thanking to all the resource persons, all the especially Sadhar sir and all other my colleagues, my principal, for supporting me for organizing this lecture series. Now, finally, I request one of the sincere most member of our chemistry department, Pavitra Behera Abu, to propose a vote of thanks, formal vote of thanks. Pavitra Abu, unmute yourself and give the vote of thanks.
I thank Devasis sir first for arranging such nice talks, and Himanshu also give a very good talk. He has shared this in Facebook. Hope we will be helpful by this talk. And my teacher, Sasodhar sir, was there and listening to it. I also thank him. Thank you.
And Sudhan sir was also listening to a talk. He has messaged me in the WhatsApp.
Oh, I am highly grateful. They are both my teachers, direct teachers. I have studied spectroscopy from them only. So it's a great opportunity for me to present a small talk in front of them. It's a great opportunity. Thank you. Thank you for giving this opportunity, Devasis. Thank you.
Now, Pavitra Abu, propose the vote of thanks.
I am audible.
You are audible.
Good evening to one and all of the participants present in the webinar. I never thought I will get an opportunity to give vote of thanks such eminent person like scientists and scholars and teachers. On behalf of the chemistry department, Dhenkanal Autonomous College, Dhenkanal, I would like to express my gratitude to all esteemed delegates of the webinar for their contribution to make this webinar a grand success. I extend my gratitude to Professor Ranjit Kumar Pradhan, Principal Dhenkanal Autonomous College, Dhenkanal, as his constant inspiration to conduct webinar. I extend my gratitude to Dr. Surekha Warrior Singh, who has inspired us through his presidential speech of today's seminar. I would like to give special thanks to Dr. Sanjit Mahapatra, Assistant Professor Economics and Deputy Controller of Examination, Dhenkanal Autonomous College, Dhenkanal, who presents in the webinar and gives his introduction about the scholarship and the resource persons. I would like to express my gratitude to Dr. Himanshu Shekhar Biswal, Associate Professor and HOD Chemistry, Niger, Bhubaneswar. Sir, thank you. Your virtual laboratory experiment learning must help the student for future research and for their research and careers. I would like to extend my gratitude to Dr. K.S.K. Bharadwaj, Associate Professor and HOD Chemistry for Ravenshaw University, Sir, we are very much thankful to such a very much interesting learning experience to the future scientists or future experience, future research persons. I have some special gratitude to our great teacher, Dr. Sasadhar Samal, because his regular inspiration to his students is marvelous. I personally appreciate it. Who said there is no Gurukul here? This is the reflection of Gurukul. I feel it because now in our seminar, webinar is a real mixture of only teacher and student. Thank you, sir. I would like to extend my gratitude to our beloved HOD, Dr. Devasis Mohanty, Assistant Professor of Chemistry and convener of the webinar. His constant effort and innovative idea, this webinar became grand success. I must thank to all the students who joined in the webinar to make the webinar successful without whose absence or without their meaning, webinar is meaningless. Thank you, sir. Thank you all. Over to.
Thank you, Pabitra, for nice vote of thanks. So with the word that this is not the end, this is the beginning, and we will organize much more seminars and webinars for the students of our state. Thank you all. Now I am signing off. Thank you.